ahead and get started with part 3. I'm hoping to get through this whole part today, so we'll see. Actually, I've done a little bit on the board to kind of give me a head start. I've never done that before, so let's see if it actually works in my favor. So we've been talking about reactions that are in equilibrium. They go from left to right and right to left, and we know you can write equilibrium constant expressions with them. And so Kc is equal to the molar concentration of the products, raised their stoichiometric coefficients, divided by the molar concentration of the reactants, raised their stoichiometric coefficients. So there's these cool set, what are they called? They're called solving equilibrium systems. It is so awesome. It's like a mathy thing, I think. So basically, you can come up with determinate equilibrium concentrations. The concentration of all species at equilibrium can be calculated. Okay, so notice I have in my own brain, these are going to make sense later, but we can come up with equilibrium concentrations. Okay, if we know the initial concentrations of everything, okay, and then one of two other pieces of information. Okay, that second piece of information, either you know the equilibrium concentration of something. Now, as I've written these, actually here in a minute, we're going to make columns of reactants and products up here. So you need to know the equilibrium concentration of anything, a reactant or product. And if you know that and the initial concentrations, you can solve the system. Or if you know the Kc and the initial concentrations, you can solve the system. I'll show you what this looks like. We're going to start with the first one. Okay, so the first one says you know initial concentrations and you know the equilibrium concentration of something. These are called ice charts, ice diagrams. Can you see the ice? Okay, initial, change, equilibrium. I really like them. Okay, so the way we're going to kind of backtrack to the equilibrium concentrations of everything is through stoichiometry. I'll show you what that looks like. It's easier to show you than to describe it. So we're going to look at this one we've been looking at before. The nitrogen combines with hydrogen to form ammonia. We can actually, let's see how I want to do this. Okay. So it tells us we start with initial concentrations of 1.00 molar for each of the two reactants. So I'm just going to go ahead and on my ice chart, I'm going to go across the top and I'm going to make these columns for the two reactants, molar concentration of N2, molar concentration of H2, and the molar concentration of NH3. Of course, that's the product, and these are two reactants. Okay, and then I'm going to start putting stuff there. Suppose the initial concentration of both of the reactants are 1.000 molar. So that goes right there. It's like a table. Okay, the initial concentration of ammonium is 0. Ammonia, excuse me, is 0. All right. It goes on to say, when equilibrium is reached, the concentration of N2, so equilibrium concentration of N2 was 0.921 molar. So here in a minute, do you think you can get the change? By subtraction, right? Okay, and actually the change here is related then stoichiometrically to this change and this change. Okay, so that's exactly what we're going to do. So the point here is to come up with the value of equilibrium concentrations, the other two equilibrium concentrations, and the value for Kc. So here to stay is writing equilibrium constant expressions. So in this case, we would say, and I think it's on the next slide, it's ammonium squared, squared, divided by the molar concentration of N2 raised to the first power times the molar concentration of H2 raised to the third power. Okay. So when I'm working a problem like this is kind of how I just put it all out there. Okay. So our Kc expression for this equilibrium is this. It's kind of a bird's eye view of what's going on, I think. So, how much of, let's see, how do I say this? How much N2 reacted? Well, we can take 1.00 and from that subtract 0.921. And you know that 0.079 moles per liter of N2 reacted with a certain amount of H2 that was there to form ammonium. Okay? So right off the bat, and I didn't write down the stoichiometry. Oh, there it is at the bottom. Do you buy that for every 1 mole or mole per liter or mole per liter of N2 that reacts, 3 moles per liter of H2 reacts? So bada boom, I can actually take this times 3 to get this change. Doesn't that make sense? I think so. If I take 0.079 moles per liter times 3 moles of H2 over 1 mole of N2, I get this change must have been 0.273 moles per liter. Now how can I get the equilibrium concentration of my H2?
Just by subtraction.
Just by subtracting, exactly. And one of the things I'm probably a little bit sloppy at is that actually is a negative change. Sometimes we have a positive change. This was a negative change. Yep. Yep, we're going to get it by subtracting. That's exactly it. And then how would this change be related to the NH3 that formed? A factor of 2. And actually in this case it's 2 times. So I can take this times 2 over 1 to get this change. Yep. And that's going to be a positive change. Oops. Cool. And we're almost done. See, I really like the tables. Now, instead of table form, actually this is not table form. My slides aren't right now. Okay? So, of course, the little subscript means equilibrium concentration. Bless you. We can get the equilibrium concentration of the H2 by taking the initial concentration, what we say, applying the change, which is a negative 0.273 moles per liter, and you get a 0.763 moles per liter. And we're going to do a similar thing with ammonium, although it started out at 0. So 0 plus 0.158 is 0.158. We good with that? I am. And then all we got to do is take these 3 equilibrium concentrations, I'll put little e's here, and plug them into our Kc expression. We're done. Dun, dun, dun. So Kc is equal to 0.158 squared divided by 0.921, also in the denominator 0.763 raised to the 3rd power. Of course, you recognize those concentrations as equilibrium concentrations in our bottom row of our ice table. Voila! So that's our value of Kc. They're done. So, I must be talking really fast. But anyway, we'll take a look at these right quick. I was looking at them. I didn't look at the other side, but I did look at these. They look like this. So I know sometimes chemistry problems, it's like a lot of blah, 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 a lot of words. So you have to extract out from the problem. You kind of see the chemical equilibrium kind of embedded in there. So I really like to take the equilibrium, write my equilibrium constant expression. Whether I use it or not, it just gives me warm fuzzies. Okay. So I'm getting ready to do my ice table, my ice chart. Initial change, equilibrium. Now, as is the case, oftentimes you're given moles and volume and you have to come up with molarity. Don't go just with moles because that ain't going to do it for you. Okay? These are molar concentrations up here in your equilibrium constant expression and in your ice chart. So you can do that. Notice that in this case, we don't have any product when we start out. Sometimes you have to read it a couple times to get that. I do anyway. The thing in red, if you read it a few times, that 9.65 times 10 to the minus fourth, that actually is the equilibrium concentration of one of the products. Okay, so you know that. So then right away you can come up with this change, can't you? And use stoichiometry to come up with these changes. Take their initial, apply the change, and come up with equilibrium concentrations. That's it. So it's kind of whatever you have, you run with it. Now, in this case, the stoichiometry is one across the board, so the changes are all going to be the same, but the changes for this reactant is going to be negative, and the changes for the two products actually is going to be positive. So you take the initial, apply the change, and come up with equilibrium concentrations. Add them down, and then plug them back into your case expression. So here's one for you, a different equilibrium. I kind of wrote it down there because it was like carried over. You're like, seriously? Okay, so in this case we are given determine the value of Kp. Oh, we're supposed to come up with the value of Kp. And what I'm going to show you is I'm going to get Kc first. So the difference between the two is that in Kp, we're dealing with the partial pressures raised their stoichiometric coefficients. Now, in this problem, if you read it, we can't get to partial pressures, but we can get to molarities. So let's go Kc and then fix it at the end. We can use those masses, and you're going to have to convert those masses to moles and then divide by the volume. You can do that. Good Gen Chem 1 stuff. There's my ice table. We have two reactants, one product. This one's kind of fun because look, check it out. We have a certain amount of one of the two reactants and a certain amount of product initially. That's kind of fun. You don't have to just have two reactants and no product. I think so. Okay. The equilibrium concentration that's given is for the product. And we can get that from, I have my notes here, the moles and volume. So once we have our one equilibrium concentration, we can get the change in that particular species and then backtrack to the changes in the other two things in this case. Now, stoichiometry is not the same across the board, so you're going to have to make sure you do that right. But in this case, notice that we are going to, this might not be entirely obvious, but you'd be like, well, which way does it go? Well, it's going to have to go to form more of this being the product, because you don't have any of, no, it's going to go to form, I don't know what it's going to go form. B. Why do I have an increase in H2S? Oh, I guess so. So it's going to go from reactants to products. So your initial concentration of your H2 is going to decrease. S2 is going to, oh, because increase. I'm not sure about that. I'd have to double check. If there's an issue, let me know. But it's like the pattern we've been doing. You take those equilibrium concentrations, plug them into your Kc, and then you're going to have to do one more thing that we talked about earlier, which is go from a Kc to a Kp. Are you looking at my pluses and minuses too? It seems like...
It doesn't make sense. Why would, yeah, because the H2 and the S2 are on the reactant side, so why would one be negative and the other positive? And then you're showing as the S2 having an initial concentration of 0.
seems like this would decrease, and these two would increase, because that's the only way you can go. I'm kind of thinking, I'll put red what I'm thinking over my green. What I really think right now anyway is I think it's going to have to go from products back to reactants. Is that what you just said? I think this is going to have to be negative.
Like, I wasn't exactly sure which way
Positive.
it went, but it wouldn't make sense for the S2 to be one thing and the H2 to be another thing.
Yeah, right. They're either both gonna, they have to go the same direction. Did I get the equilibrium right? Let's see. H2. Determine the KP. If it's not at equilibrium, and there's none of this, to get some of this, it has to go from right to left. And if it does that, this is going to decrease, increase, increase. So in red, I kind of put what I think it is. That's the only direction I can see it would go. So, and I'll try to remember to double check that. Today's Friday. If it totally freaks you out, you can always contact me over the weekend. But I'm changing my green. Oops. One more. Come back here. All right. The next one, or the last one, yeah, looks like this. What hints do I have here? Oh, my hint here is a red number 2. Can you see where, well, not just the red number 2. It's given in words, and you have to translate it to an equilibrium. You know what I'm saying? So you have to balance it in order to know what the equilibrium constant expression is going to be. You cannot make an equilibrium constant expression without an unbalanced equilibrium, right? So that's kind of my hint there. So here's my ice table. Initial change and at equilibrium. So in this case, it's a little more straightforward. You don't have any products, you just have some reactants, so it's going to have to go from left to right. Looks like from what I have here, you're given the equilibrium concentration of one of the two products, so you can get the change and then apply that change to the other product and the reactant. Now let's see if I got this one right. Yeah. This one actually will decrease, this will be plus, and this will be plus.
So do we know which direction it goes then by if their initial concentration is 0?
Yeah.
Okay.
Yeah, she asked, do we know if the initial concentration, do we know which direction it goes by, you have to form something that's 0. Yes. Yep. So this one is minus, this one's plus. Is that my last of my, almost? Okay, just kind of like what we've been doing. Substitute, chug and plug and chug. Okay, now we're ready to go on. So the second type of problem, solving a system in equilibrium, is where you are given the initial concentrations of everything, and you're given Kc. Now, of the two, this one can get a little more interesting. You're going to end up using the quadratic equation, which, I don't know. So I'll just kind of talk you through it. Basically, we're going to come up with a variable. I'll go over here because this is where we're going to be drawing these two. We're going to come up with a variable x, and we're going to make all the changes in terms of that variable x. And then once we do that, we define what our x, whether it's plus x or minus x, we make the other species in terms of x, depending upon their stoichiometry. And then what we do, so we have initial concentrations, we have changes in terms of x's, it's just like we did over there. To get the final, we take the initial, apply the change to get the final. Initial, apply the change to get the final for all the species involved. Then what we do is we take these equilibrium concentrations and we plug them back into our Kc, our equilibrium constant expression. So all of these are going to be plugged back into our Kc. You know the value of Kc. Now you have some blob over here in terms of just one variable x. And you should, if you have one equation, only one unknown, be able to get to that unknown. That's it. Solve for x. Yeah, boom. Almost. So then once you have x, we're going to plug that x back into these quantities down here, because these values were in terms of x, to get the a real value without the x. Equilibrium concentration. So that's kind of what it is. Boom. So we're going to pick on this one. So I'll go ahead and jot this down. Our Kc expression for this one, and I'll go ahead and start in writing my columns. Kc is equal to, is always products over reactants, molar concentration of HF squared, divided by the molar concentration of H2 raised to the first power, and also in the denominator the molar concentration of F2 also raised to the first power. And we have a value, we have a winner, we have a value of 115 for that. So for my ice chart, I usually take it just, I usually write reactants here, molar concentration of H2, molar concentration of F2, molar concentration of HF. Then this slide, the next slide, takes those moles and volume to get molarity. Don't be caught working this sort of problem using moles. It has to be moles per liter molarity. So here we go. That's what I said. That. So here are my molarities. So in the original problem, we were given 2 moles H2 floating around in a container of 2 liters. So I'm liking 1.00 moles per liter for my H2. For fluorine, the original problem said the initial amount of fluorine was 4.00 moles divided by 2.00 liters. I'm liking 2.00 moles per liter. And the initial concentration of the product was 0. So here comes the X part, and my hint is to choose something that has a stoichiometric coefficient of 1. So we could choose either H2 or F2, but if we go ahead and make the change of H2 be equal to X, and let's go ahead and it's going to have to be negative X, right? Since it's in a 1-to-1 relationship with F2, what would this change be? Yep. Nope. It's a 1-to-1.
Just negative x.
Yeah. Is that what you said? I thought you said 2x. And the HF would be. It's got a.
The 2x?
Oh, okay. Plus 2x. But I said anyway. I think we're all on the same page. That's the important part. Okay. Cool. Well, the next thing we do is actually, and I kind of said this in the outline, is take the initial, apply the change, and get our equilibrium concentration. So the H2 is actually, I'll forget the M for now, but at 1.00 minus X. Okay, that actually is the equilibrium concentration of H2. The equilibrium concentration of F2 would be that 2.00 minus X. And the equilibrium concentration of HF would just simply be, well, I'll go ahead and do it this way. 0 plus 2x, or 2x. Okay? The next thing you're going to see the slides do is to take these quantities and plug them in. okay? I don't know what you want to, so I'm kind of deviating from my slides here. So my slides say. And it looks like a mess, but if you're not a math person, yes. I'm not a math person. Okay, so my slides, I like the ICE tables because they keep me organized, but you actually can work this problem without an ICE table. You can come to the same conclusions with setting, the other thing is I'm all about communication, and that's not, shouldn't just be for me, it should be for all scientists, especially physical scientists. To communicate the answer to your problem, you have to tell me what X is. And even, to me, if you use an ICE table, you're telling me what X is. If you choose not to use an ICE table, especially on the exams, and you just introduce X, I have no idea what your X is. So if you choose to do that without an ICE table, you're going to need to do something like this. Let X be equal to the change in molar concentration of, pick one with stoichiometric coefficient of 1. Okay. So those are our equilibrium concentrations. Here is the ICE table that I've been right away already kind of working with. All right, so we're ready to substitute in, and it looks like this. Okay, so it would be in the numerator, it's 2x quantity squared. In the denominator, we have two terms, that quantity 1.00 minus x, and also in the denominator, quantity 2.00 minus x. And I debated, but I'm going to kind of show you, maybe some of you don't need this, how we flatten this thing out. Kind of drives me nuts. Let's see. And they're nice, easy numbers. The 2, the 1, they all kind of work in our favor. So don't forget, for instance, that this will actually help you down the road. That square applies to the number and the variable. So I can start by, in my numerator, it's really 4x squared. We good with that? In my denominator, and some of you are probably better at this than I am, it's kind of the smiley face thing, where I'm going to actually multiply these two terms together. I'm going to take the number 1 times 2, and of course I'm going to get 2. I'm just going to round it to, I'm not going to worry about the decimals at this point if that works for you. I'm going to take kind of these two terms, this term right here and this term right here, and to me I'm going to get a minus 1x, combine it with a minus 2x and get minus 3x. And then I'm going to take, this is, I know I'm totally butchering this, but I'm going to take this term, my minus x, times my minus x, which actually I'm going to get x squared. And that quantity is all equal to 115. I'm flattening this out so I can get it in standard form. I usually think of that 115 over 1, because then I cross multiply and flatten it out that way. So I basically have my 115 times this mess is equal to 4x squared. So, running out of room. So 115 times quantity 2 minus 3x plus x squared is equal to 4x squared. The standard form has 0 on the right, okay? So I need to get 0 on the right. So to me, before I do that, I need to take this 115 through that. So 115 times 2, of course, I'm totally running out of room, is 230. I'll do it up here. So I got 230. See, 115 times 3. I got 345. So 230, and that's a negative 345x. And then I take that 115 x squared. All right, is equal to Dun, dun, dun. We're getting close. 4x squared. Sorry, it's so sloppy. All right. So I think, yeah, standard form has the x squared term first. So x squared, x, and then nothing. So I'm going to go ahead and kind of move towards that. So if I take my 4x squared to the other side, I subtract, so I'm get what, 111x squared, okay, minus 345x plus 230 is equal to, or 0, excuse me. What do you think? That's flattening it out, getting it to standard form. Yay. Okay. I'll try to kind of show you as we, how do I say this? Yeah, I think I'll probably wait till the next problem. But I'll show you where on a test you can stop. And for your homework, you have to do this, okay? For a test, you don't have to do this. And I'll try to kind of show you how that works. I can probably show you right now. For a test, what I need to see is that you can substitute in those equilibrium concentrations. Just substitute them. Leave the X value in there up into those molar concentrations. Then you're done. For homework, you have to take it to fruition.
So for the test, if we just got it to the 2x squared over 1 minus x times 2 minus x?
Yes.
That'd be fine.
Yep, and I'll try to communicate that to you.
So you're just concerned about the chemistry part, not the math part?
Right, yes. But for your homework, it's going to be the math part too.
We can pretend it's...
So let's take a look at the math part. Let's see if I want to. The quadratic, I don't like it. Some people love it. Sicky. So yeah, this is the standard form that we got it into. And notice that this only works, the quadratic equation only works for a binomial, okay? This then, in blue, you don't have to use this on your test. And actually, I have a website out there to show you that, heck, for your homework even, if you have access to a computer, you can just plug these, you can go to online and ask for a quadratic equation solver and just plug them in. But what you might remember is actually we get 2 solutions to this. And the 2 solutions come in, you plus this square root and you minus the square root, and you get 2 values for x, 2 solutions for x. And what we're going to find out is one solution makes sense and the other solution is bogus. Okay. Yep, just like that says. Okay, so back to the problem. It looks like this. So we're going to plug the 111 is A, negative 345 is B, 230 is C. So it looks like this. This bad boy. Ooh. Like I said, some people are like, oh, I love the quadratic. I'm like, are you serious? So it all kind of looks like that. Okay, or just use the online program. Now there were several out there, and I kind of picked the first one that came up, and it looks like this, which isn't bad. This isn't the one I used. This looks like a different one. Okay, so somebody tell me what A is.
111.
Thank you, 111. And B is,
Negative 345.
thank you, negative 345. And C,
230.
thank you, 230. There you go. Those are your 2 answers. And I have a slide coming up, but which one of those doesn't make sense? Now that's going to be our negative x. So your options are, that's going to be our x.
You go with 3 sig figs on this?
Sig figs, I think I just go with, I think I go 2 decimals. Maybe I go 3 sig figs. No, I can do 3 sig figs. But does this make sense? I'll answer my own question. If we went with a value of 2.19, you're like, Well, that doesn't make sense, because we don't even start out with 2. You know what I'm saying? Or we start out with 2. So 2.19, you can't subtract more than you start out with. So in this case, the real one is the other one. So here we're gonna finish out the problem, basically taking that, what is it, 0.9 something, and we're gonna plug it in, and we're gonna come up with equilibrium concentrations. That's it.
So it'll always work out where one's too much.
Yep, 1's too much. Yep, yep. You got it. Oh, yeah. So this other one, I guess I have 2 of them. This one is different. That must have been from last year. So anyway. But if you just Google it, right, I think I posted one on Twitter. And also, I was like, oh, I could be really cool, and because this will do it too, but I got lost. It didn't, I don't know. So there's,
Yeah, I think mine does that too.
yeah. I used to be able to do it, but I couldn't do it today, so I bailed on it. Yep. The only one that makes sense is the one that's small enough to make sense. Yeah, 1's too big. So let's finish up the problem. And finishing up the problem, we substitute back in our value for x now. And this first one, I'm like, really? How's that work? Well, since we're subtracting that last little bit, we're subtracting, so we have to go with decimals. So I know I've got 2 decimals and 3 decimals, so I only allow 2 decimals. Okay, so that's the equilibrium concentration of the first reactant, equilibrium concentration of the second reactant, equilibrium concentration of the product. So now you guys see how we can get our, well, oh, this is another cool problem. See, so you can check your answer. How, can you see how we can check our answer?
Yeah, you just plug them in, and if it's 1.
Yep, you just plug them in, and if it's 115, you're like, ah, I must have done it right. If it's not, you're like, ah, hopefully it's close enough. All right. Well, let's take a look at the next one. And we're going to do it the same way. I don't think there are any, the only thing that's different about this one is the numbers aren't as pretty. Okay? So, and I look at this one, so the significance of uppercase, lowercase. So what is CO? Like, how do I say this? Uppercase O. What's the? Carbon monoxide, yeah, exactly. So don't look at this and get in a hurry and say, well, that's cobalt and bromine. So no, that's carbon, oxygen, and 2 bromines. So let's see what I want to do. There's the questions. I'm going to go ahead and on the next slide, I'm sure you see the equilibrium constant expression. It's the molar concentration of the products, CO and Br2. Raised to the first power, and on the reactant side we get COBr2. All raised to the first power. That's kind of nice. I guess this one does have a twist. Notice that we have a little bit of everything, and that's what we were talking about a minute ago. If you have 0 of anything, it's going to have to go to form some of that. In this case, we've got a little bit of everything. So right off the bat, we're going to have to find out which way it's going to go. In part, this is part 3, in part 2, how did you figure out which way it's going to go?
The relationship between Q and K.
Yep, the relationship between the snapshot Q and the equilibrium constant, which is given K. Yeah, this one's given is 0.190 exactly. All right. So we can go ahead and, for instance, oh, I didn't write these up here. Oops, COBr2. Where that's our reactant and those 2 are products. Okay. So the equilibrium constant expression is that, and your your reaction quotient expression is also that. But instead of Kc, it's Q. So we're going to have to take those masses and use molar masses to get moles, and then divide by volume to get molarity. So here's what that looks like. I'll just put all three of these up here. Do you guys have these? Okay, this is Gen Chem 1 stuff. So we have the initial molar concentration of everything, 0.79 moles per liter, 0.295 moles per liter, 0.454 moles per liter. Okay, ready to plug those into a QC, excuse me. Your reaction quotient then, they're all raised to the first power because that's what their stoichiometric coefficients are. We put 0.795 times 0.295 divided by 0.454. And that gives us 0.517. So it's too big, right? So which direction do we need to go?
Or more reactants?
To form more reactants, exactly. So now you're going to be minus x, plus x. By that, that's what we know now. All right, very good. Reaction must go from products back to reactants. So now we're almost done. So if I stick with my ice chart, it's going to be, this column is going to be 0.795 plus x. This column is going to be 0.295, minus x. And this column is going to be 0.454 minus x. And then the messy part comes in. We take this and plug it into there, and these quantities go up here.
Would it be 0.795 minus x? That's what it is.
0.795. No, it goes back to form. Yeah. Oh, but see, I have my columns are different than these columns. So, yeah. What he's saying is this: the ice table has the columns turned around, or my ice table, however ice table you want to look at it. But so.
I think he's got the value because he's got for BR2 where yours is the 295. That's weird for that, right?
Yeah, and that's 295. Same thing.
Yeah. Yours says 0.454.
I think you might switch the value.
Oh.
When you wrote them.
Yeah, I think.
Oh, these are switched?
Yeah.
Okay, thank you. So like a student. Like that? Okay, thank you. Very good. So, yeah, I don't know why, and this is like a textbook thing, I think they put the reactant, they put the products and then the reactant, and I usually put the reactant in the products. So. Okay. So, substituting it would look like this, and just so we're on the same page, you can put the word stop here if you want on the test. Stop here on the test. You'd be done. Grins all the way around. But for the homework, you have to keep going. Okay. And if you keep going, you're going to find actually it looks like this in standard form, where A is 1, B is -1, 1.280, excuse me, C is a positive 0.148. And when you solve for the two roots, you come up with dot, dot, dot. One will make sense and one will not. Your two solutions, which one should we go with? Oh, I'm serious. What do you think? Yep, the smaller one again, 0.129. Yep,
Seems like it's always gonna be the smaller one.
it seems like it. I'm trying to think if there's ever been a case when it's not. I don't think, I
Because
don't
no
know.
matter how small the number is, you always have that much.
Well, I think, and I could have this mixed up with something else in chemistry, but I think sometimes you get a negative solution, and a negative X is not a possibility either.
And you said there's never a situation where they both will work?
Right, I know that. Yeah. And what I don't know is if it's always small or not.
Oh, well, hopefully tomorrow we'll figure it out.
Yeah. So plugging back in then, we get something like this. See if I can fix my issue over here. What's that? A lot of sixes on the slide. The CO molar concentration, I'll just pretend like it's correct up here. Zero 0.666. The BR2, 0.166, and the reactant, 0.583. No, that's not right, is it? Oh, crap. So,
I think the 0.454 is supposed to be
Yeah.
for the
Yeah,
CO
if you just
BR2.
switch the label, like put BR2 where CO is, and flip those,
Well,
you'd be right.
this is right here, no.
Yeah.
Oh,
It actually
And
goes
then
here.
your CO has a 0.795.
that was squirrely.
Yeah. I totally butched that. Sorry, guys.
That's
Okay. But are we up against a assignment slide?
Yes.
Okay. Okay, so your assignment slide, I'll just push the things out there.
Sounds good.
Yep. Well, hopefully next year I won't, that will work for just fine.